Hi everyone, in this video we're working through question 8A part 2 of the 2004 unit HSC exam. So it follows on from my most recent video where we worked through part 1. So this part 2 says to let z equal cos theta plus I sine theta for theta between 0 and 2 pi. By considering the imaginary part of the left hand side of the equation in part 1, deduce that the sum from k equals 1 to n of sine theta plus sine 2 theta all the way up to sine k theta, show that that's going to be equal to n plus 1 sine theta minus sine n plus 1 theta, all divided by 4 sine squared theta on 2. And we're told that we can assume that z on 1 minus z equals I on 2 sine theta on 2 times bracket cos theta on 2 plus I sine theta on 2. So quite a complex looking result that we're being asked to derive, but we're kind of given the scaffolding that we're basically going to be making use of part 1, so that's a good place to start. So here I've written out the result that we're being asked to show. That'll be helpful to take a look at and make sure we're kind of heading in the right direction. But to kick off this question, we're given the hint to go and take a look at part 1, which we've just worked through in the prior video, and have a look at this result, and in particular look at the imaginary part of the left hand side. So let's go and do that. So let's have a think about, well, what is the left hand side? So the left hand side of, I'll just call it part 1, the result from part 1, well, that was equal to the sum from k is equal to 1 to n of z plus z squared all the way up to z to the k. But we've just been told to quite specifically let z equal cos theta plus I sine theta, which is one of the common forms of a complex number. So let's just throw that in. So what that's going to be is the sum from k is equal to 1 to n of, and we'll have z, which is cos theta plus I sine theta, plus z squared, which using de Moivre's theorem, we know we can write as cos 2 theta plus I sine 2 theta. And we can keep going, and we'll get to z to the k, which again with de Moivre's theorem is cos k theta plus I sine k theta. So that's the left-hand side expanded into this format, but remember we're only really concerned with the imaginary part, and what that really means is just the bits that are linked to I. So I'm just underlining these here because really that's what we're going to focus on, and you may notice that is the left-hand side of the result, because if we now say well, let's just say, therefore, the imaginary part of this left-hand side would just be equal to the sum, still the sum from k is equal to 1 to n, that hasn't changed. But we're just going to write out these underlined bits, these bits that are linked to I. So we'll have sine theta plus sine 2 theta, and so on, all the way up to sine k theta. And that's a good start because that is exactly the left-hand side of the result that we want to show. So basically, where this question is really leading us is to now basically go, well, looking at the imaginary part of the left-hand side from part 1 got us what we needed. So how about we look at the imaginary part of the right-hand side of that result and see if that also gets us to where we need to be. So that's what we're going to do. And just like we did here, we'll start by looking at the whole of the right-hand side, and then we'll hone in on just the imaginary part, and then we'll set them equal, and hopefully we get what we need. So if we say, well, what was the right-hand side of part 1? And I'll just refresh myself. So it was nz on 1 minus z. So equal to nz on 1 minus z. minus z squared on 1 minus z squared, so minus z squared on 1 minus z squared times 1 minus z to the n. So that's kind of what we're dealing with. Now, I think it's helpful to remind ourselves of this note that the question gave us, which is that z on 1 minus z can be written as I on 2 sine theta on 2 multiplied by cos theta on 2 plus I sine theta on 2. And I think that, again, if we think about, well, what is cos theta on 2 plus I sine theta on 2? That's basically, again, using de Moivre's theorem, that's just z to the power of a half. So I think it might be helpful to really point out that that is I on 2 sine theta on 2 times z to the power of a half. So let's just keep that note off to the side, because if we're being guided to think about z on 1 minus z, I think it's helpful to really expressly highlight where the z on 1 minus z's are in this right-hand side, because I think that's kind of the hint. So let's just really make this clear that this right-hand side can be written as n times z on 1 minus z. That's this bit, minus, and maybe I'll just write the 1 minus z to the n times, and here it's z squared on 1 minus z all squared, which really we can write as z on 1 minus z all squared. And I've quite deliberately done that because I want to highlight the z on 1 minus z's so that we can now insert this bit here. So let's do that. So that's equal to n times I on 2 sine theta on 2 times z to the half minus 1 minus z to the n times, and here we need to put all this, so that's I 2 sine theta on 2 times z to the half, and that's all squared. Alright, so now let's see if we can clean this up a bit more. So it's going to be equal to, basically, maybe I'll just write this as n I z to the half on 2 sine theta on 2. And then I'll just write minus 1 minus z to the n, and let's just focus on squaring this. So it's going to be times I squared on, squaring this will give us 4 sine squared theta on 2, and then z to the power of a half squared will just end up with z to the power of 1, since a half times 2 is 1. Alright, it's probably enough room for one more line of working before we have to turn over. So maybe, I think, because what we're working towards has this 4 sine squared theta on 2, and I've seen that once here, so we've got that in the denominator for one of our terms. I think it's going to be helpful to get it as the denominator for both of these terms, so that we can then see how we can get things simplified. So let's get this common denominator. So we'll say that's equal to, I'm going to get 4 sine squared theta on 2 as my common denominator. To get that as the denominator here, I'm going to have to multiply top and bottom by 2 sine theta on 2. So this will be 2 sine theta on 2 times n times I times z to the half, and then the minus, well, this I squared is actually negative 1, so negative will be plus 1 minus z to the n times z, and that's now all over this common denominator of 4 sine squared theta on 2. So now, how do we simplify this? I'll probably have to turn over just to make sure there's enough space. So let's keep going. So we'll just come up here and we'll say which is equals. So still we're dealing with the whole of the right hand side. We haven't focused on the imaginary part yet. But let's say that's, how about we bring out this 2n sine theta on 2. So we'll bring the, or maybe we'll bring the n out first and then 2 sine theta on 2. That might end up being a bit simpler. So n times 2 sine theta on 2. And then we've got this I times z to the half. Now, I think at this point, it might be helpful to start taking these z's and, actually no, let's leave it as z to the half now, and maybe in the next step we'll start to put the z's back into cos and sine theta. So we got n times 2 sine theta on 2, z to the half times I. Can't forget about that I. And what we can do is expand this bracket. So it'll be plus z minus z to the n plus 1. So we'll get plus z minus z to the n plus 1. And that is all still over 4 sine squared theta on 2. Alright, now as I mentioned, because we know z is cos theta plus psi sine theta, and because the result we're working towards doesn't have z's in it, it's just got the sine thetas, at some stage we're going to have to put this back into that form of cos theta plus psi sine theta. So now is probably the time to do it. So we're going to have n times 2 sine theta on 2 times, now z to the half using de Moivre's theorem will be cos theta on 2 plus I sine theta on 2. So cos theta on 2 plus I sine theta on 2 times I, can't forget that I, plus cos theta plus I sine theta, that's our z, plus cos, now I've got to make sure there's enough that we can see everything here. So cos, now z to the n plus 1, so that's going to be n plus 1 theta plus I sine n plus 1 theta. Alright, so that's the top. And remember, that's all over our common denominator of 4 sine squared theta on 2. Alright, now I think there's one step where if we can put this I, expand this I into this bracket, we'll then probably be in a place where we can hone in on the imaginary part of this right hand side. So let's say it's n times 2 sine theta on 2 times, so we're going to get the I cos theta on 2, and then the I times the I will be I squared, which is minus, so minus sine theta on 2, and then we've got our plus cos theta plus I sine theta plus cos n plus 1 theta plus I sine n plus 1 theta, all over our common denominator. Alright, now I think we're in a good place where we can just highlight, well, what are the imaginary parts of this? Because that's what we're going to equate. So here the imaginary part, it's anything with an I in front of it, so it's going to be this cos theta on 2 multiplied by this here, because that's what you get when you expand the brackets. Expanding this bit, we'll leave that as real, so we don't want that. We don't want this, it's real. We've got our sine theta, don't want that, and then we've got our sine n plus 1 theta, all over this common denominator. So let's just hone in on that. So we say, therefore, the imaginary part of the right hand side is going to be equal to, so n times 2 sine theta on 2 cos theta on 2 plus sine theta plus, just got to make sure. I feel like I've done something silly here. So we actually, if I notice there's all pluses here, but look at this minus. So it's minus z to the n plus 1. So cos theta plus I sine theta, that should be minus cos n plus 1 theta minus, yeah, so I nearly made that mistake. The only thing that made me think of that was thinking back to this result, there's a minus there and I wasn't seeing a minus. And so yeah, that's what highlighted that. So that should be minus sine n plus 1 theta. And then again, all over our common denominator of 4 sine squared theta on 2. And now if we look at what we're dealing with here and what we're trying to work towards, we're pretty close. I mean, we've got our sine n plus 1 theta, and we've got our denominator. So it's really just this part that needs to simplify. And notice that what we're working towards is an n plus 1 sine theta, or in other words, n sine theta plus sine theta. Now, we've got our plus sine theta, so is this here n times this? How do we show that that's actually n sine theta? And maybe I'll just work off to the side, maybe in red. We're going to hone in on this bit. And I think we can make use of the result, basically sine of 2x, say. In general, you'll see the result as sine 2x equals 2 of sine x cos x. And so that would mean sine just of x by itself would be 2 sine x on 2 cos x on 2. In other words, I've just halved all these angles to get x. And then we're dealing with thetas. So what that really means is sine theta is equal to 2 sine theta on 2 cos theta on 2. So what that means is if we've got 2 sine theta on 2 cos theta on 2, we can replace that with sine theta. So actually this imaginary part now simplifies to n sine theta plus sine theta minus sine n plus 1 theta all over 4 sine squared theta on 2. And now we're really close. We just need to factorize this sine theta. So it's n plus 1 sine theta minus sine n plus 1 theta all over 4 sine squared theta on 2. So that is what we've got. So now we can do our final conclusion. Therefore, by, how do we say it? Let's say by equating imaginary parts. And I think we do need to highlight to, say, an exam marker that this is why, like this is the whole reason for our approach. We can now set the imaginary part of the left-hand side, which is this bit here. The sum from k is equal to 1 to n of sine theta plus sine 2 theta and so on up to sine k theta. That is equal to this here. N plus 1 sine theta minus sine n plus 1 theta all over 4 sine squared theta on 2. And that is exactly what we were being asked to show. Alright, so there you have that question. Part 2 definitely, I guess you'd call it harder than part 1. I think part 1 of this 8A was really scaffolding in. They wanted us to kind of use something fairly simple, at least in the context of 4 unit, sum of a GP, to just get this result and then make use of that result to use very much a 4 unit concept of complex numbers and equating imaginary parts to now show a much more complex result. But again, I think the key was just really staying calm and being very methodical. At the end of the day, we're just equating imaginary parts. This left-hand side was very, very simple, just inserting the cos theta plus I sine theta and honing in on what's in front of, or what's next to the I. The right-hand side, obviously a lot trickier. You have to be really careful, make use of the hint they gave. Don't stuff up your negatives like I nearly did. Although the benefit of a question where they give you the result is hopefully, just like for me, being able to notice that highlighted that I'd made a mistake. So that kind of helped. If you weren't given the result and just shown, like told to work out the result yourself, then yeah, that error is a much greater risk of happening. But yeah, hopefully you're able to follow all that and you found it helpful. And tick boom.